Okay, so let's continue with this sort of silly endeavor of trying to make little videos to help minimize the amount of time we spend talking in class. Uh, so this video I think will be about different coordinate systems. So of course the idea of a coordinate system is that you'd somehow like to represent different quantities that are spatial. One example of a spatial quantity is simply where something is. And you're probably very familiar, of course, with the idea of the Cartesian coordinate system. So the Cartesian coordinate system, if we think about 3 dimensions, you typically think about there being an x-axis, a y-axis, and a z-axis. And if we're interested in the location of some point in space, we measure sort of how far it is in the x direction, how far it is in the y direction, and finally how far it is in the z direction to come up with some set of coordinates that tell you where it is. So for example, it might be 3 in the x direction, 4 in the y direction, and 5 in the z direction. So you would say that the location of this point in the xyz coordinate system is 3, 4, 5. Or you might equivalently say that point is the vector position r, and you'd say that r vector was 3 times I hat plus 4 times j hat plus 5 times k hat, right? So that's the coordinate system that you're probably most familiar with. It's the Cartesian coordinate system. It is what's called an orthonormal coordinate system, which means that the axes are orthogonal, and probably means something else too, but I'm not going to worry about what that is right now. So that's a great coordinate system if what you're interested in has the kinds of symmetry that make the Cartesian coordinate system logical to use, and it's also a great coordinate system to use in cases where you don't have a whole lot of symmetry because it's a very convenient coordinate system to use, and it's one that we know well. It's one that we're fairly intuitive about. A second coordinate system that we use pretty commonly is the polar coordinate system. And of course, you've probably seen the polar coordinate system as well before. So we'll just work in 2 dimensions to talk about this, then we'll extend it to 3 dimensions and talk about both cylindrical and spherical coordinates. So if we think first about just in 2 dimensions, let's say we've got an x-axis and a y-axis, and we have some point r that's in the xy plane. If we were talking about the Cartesian coordinate system, of course, what we would do is we would measure how far r is out in the x direction, how far it is in the y direction, and we'd say, okay, in Cartesian, maybe for this particular point, r vector would be 4 times I hat plus 4 times j hat. Now, if we want to talk about where r is from a polar perspective, instead of measuring how far r is in the x direction, how far it is in the y direction, we instead measure what the distance is from the origin. So we measure what the magnitude of r is. So that's one thing that we need to know in order to know where this location is, and know what the magnitude of the vector is. And we also measure what the angle is, measured counterclockwise with respect to the x-axis. So we measure theta. And 2 things I'll emphasize there is it's with respect to the x-axis, and it's also measured counterclockwise. And it's often tempting to choose other kinds of definitions of theta. You're welcome to do that, but you do so at your own peril because you start to get into situations where you might, for example, find your cross products don't work right, or the things that you think should be a sine end up being a cosine, and so on and so forth. So we could also talk about this particular vector r as being represented in a Cartesian sense as 4 times I hat plus 4 times j hat. If we wanted to talk about in a polar sense, we say that the vector r is given by the square root of 32, right? Because the magnitude of r is going to be 4 squared plus 4 squared, or 16 plus 16, 32, at an angle of theta, in which case theta would be pi over 4, since of course this angle is 45 degrees, or pi over 4. So that's a sort of common way to talk about things when you've got symmetry in the situation, when you've got, for example, things that have circular symmetry. So when something's moving in circles, often a polar type of coordinate system is helpful for talking about it. Now, it turns out there's a lot of interesting stuff that happens in the polar coordinate system, particularly when you start to talk about what the directions are in the polar coordinate system. You'll notice in the Cartesian coordinate system, we talk about the I hat and the j hat components, so unit vectors that have to do with the direction of increasing x and the direction of increasing y. You might ask the question, what's the equivalent of I hat and j hat for a polar coordinate system? So what are the equivalent, what are the unit vectors for polar? And that is the question we will deal with in our next video.